personally, I think this is the most difficult module in the whole course. I know you probably aren't glad to hear that, but so I picked some of the more difficult different types of forces problems, and then next week, Miss Durden will go over like systems and slopes, which is, I think, the most difficult part of the most difficult module in the course. So luckily, I didn't get that week. um, anyway, these are our formula. We're going to kind of go through the formulas, and we'll talk about different ways of, doing force problems where you've got multiple forces in that problem. So I'm going to try and go kind of quickly. If you guys have questions, please, please, please let me know. I just want to try and work out as many problems for you as we can. So your weight is your force due to gravity. Your weight is not equal to your mass, and it's measured in newtons. Your weight is actually equal to your mass times 9.8. At this point, if you don't have 9.8 memorized, you might soon. You'll get there. And these are just a couple of images that I had that this pencil is so small, that show some weights. This book right here, so your weight is always pointed towards the center of the earth, not always down, but towards the center of the earth. So let's say, you're on an inclined plane or something like that. Your weight is going to go straight down towards the center of the earth. It's not going to go down like that. That would not show you your weight. Okay, so if we want to do a weight formula, we just do F of G equals mass times gravity, and we can just do, for this one, our mass is 65 and our gravity is 9.8, and you can get 637 newtons. So your weight is going to be much more than your mass, or your actual, like, the weight that you think of when you stand on a scale and you get pounds. It's going to be more than that as well. If we did moon's earth, it would be less. It just depends. This is most of the time you'll do 9.8 as your weight. This isn't one of the most difficult problems we have for this module, so I just kind of want to go quickly and just show you that part. So now we're going to talk about apparent weight and weightlessness, and this is where we kind of get into what I call elevator problems. And your apparent weight is the force you experience as a result of all the forces acting on it. So, like, for example, I don't know if you can see this picture. There's this guy right here. His apparent weight at that moment when that picture was taken is 0, right? Because he's like floating in the air. He's come out of his seat and he's in the air. And so that's what we consider like weightlessness. Like if you think like astronauts on the International Space Station, they're not actually weightless, right? They have weight. It's just, when they're in space, they don't have any contact forces pushing up on them, and their apparent weight is 0. So it's not like they actually have no weight, because if they had no weight, they would have no mass. And if they had no mass, they wouldn't exist. So that's not what's happening. So here's an example of an elevator problem. In this problem, we have a mass of 75 kilograms, and we are standing on a bathroom scale in an elevator. And when I used to teach in the face-to-face classroom, I was at this school that actually had an elevator. It didn't work all that well, but it was there. And we would actually take a bathroom scale into the elevator, and I would have the kids kind of measure their, their mass as their weight as they were going up, and their weight as they were going down. And they could see that actually, as they're going up, they actually weighed, a little bit less, or, a little bit more as they're going down. So anyway, in this example, we're starting from rest, right? That would be a velocity of 0. And the elevator is accelerating upward at 2 meters per second squared. So that's going to be our acceleration, and our time is 2 seconds. Now, they are giving us some things that we don't need, but that's okay, like the time. And then it's going to continue at a constant speed. And it says, is the scale reading during the acceleration greater than, equal to, or less than the scale reading when the elevator is at rest? So if we think about when the it's accelerating up, right? That means the applied force is going to be more than the gravitational force, right? Otherwise, you wouldn't be able to accelerate upward, right? So your applied force is going to be more than that acceleration force. And then if we're going at a constant speed, see if I can do like a different color. At a constant speed, these are going to be like the same. Okay, so at a constant speed, your applied force is going to be equal to your gravity force, right? And your gravity force is just your mass times gravity, right? Which is 75 times 9.8, which is 735. So that's what we're comparing to, right? Our gravity force. So when we're accelerating upward, let's look again at that, and let's look at what our net force is for this example. So your net force is the sum of the total forces acting on the system. And you'll see as we do several of these problems, we're going to continue talking about our net force and discussing, the total forces acting on the system. And that's, I think, one of the hardest parts of these problems is making sure you include all of the forces and not just, a gravity force or whatever. You're including all of these net, all of the net forces. So if we're talking about the scale when it's accelerating, right, or that net force, that's going to be your force due to your applied force plus your gravity force. Okay. And that's if we're accelerating. Okay. And so we can do this, and we can do, that's going to be MA, and that's going to be MG, right? So we can already tell if we're adding these two forces together, it's going to be more, right? So our mass is 75, and our acceleration is 2. And here our mass is 75, and our acceleration is 9.8. But we already know, that this is 735 because we just did that math. Okay, so when you add these two together, you're going to get 885 newtons. Okay, and that's because that that net force has to be more than that gravity force, right? And so you've got to have both. Okay. Let's go to a friction problem. Oh, normal force. Okay, we'll talk about that first. So the normal force, if you're keeping track of the types of forces, we had our force due to gravity, right? That was our weight. And now we have another type of force, right? There's lots of different forces to keep track of, and that's your normal force. And this is a perpendicular contact force exerted by a surface on another object. So it's always perpendicular to the surface. So, if we talk about another inclined plane again, your normal force is going to come up like this because it needs to be perpendicular, to your inclined plane. Okay, if you're sitting flat, your normal force just goes straight up. Okay, and this is basically what keeps you from falling through your chair, what keeps you from falling through the earth, all that kind of stuff, right? Because if the earth is falling down, pulling down on you and pulling you towards the center of the earth, there's got to be another force, basically keeping you up, or else you just, you'd be pulled to the center of the earth. And so that's that normal force. It's basically balances the force due to gravity. Okay, so now let's talk about friction. We have kinetic friction and we have static friction. Your kinetic friction is the friction of moving. Okay, so if you are, I don't know if you guys do this at your house or whatever, but I like to rearrange the furniture every so often. And so upstairs we have carpet. Okay, so if I'm trying to move the furniture, like I switched my kids' rooms the other day. Well, it was a couple months ago, but anyway. I like to move the furniture. So when I'm moving the furniture around and I'm trying to push their dressers across carpet, right, it doesn't work very well. So we have these things, they're called sliders. I don't know if you guys have those at your house. But you kind of put them under the thing and it has like a smooth surface, and then it makes it easier to push, right? Because now we've basically reduced the friction. That's what we're doing with those sliders. Now, when I'm downstairs, our downstairs is like a hard surface. So when I'm rearranging the furniture downstairs, we have like these little carpet pieces. They're like fuzzy and they go over our sliders. And that allows us to kind of move the furniture. I can kind of slide it and I don't have to wait for, someone strong to help me. Um, and so that friction of moving is kinetic friction. You're going to have more kinetic friction on a rough surface than you will on a very smooth surface. So like if you're ice skating, you're going to have a lot less kinetic friction than if you're trying to think, if you're rollerblading or roller skating or something like that, or walking. Um, on like a road. And then the static friction is the friction that's between two things that keeps them still. So for example, right now I have a cup sitting on my desk and there's static friction between the cup and the desk. And I have to overcome that static friction in order to push that cup across my desk. Now the cup's not very heavy and my desk is pretty smooth. So it doesn't take a lot of force for me to push that cup and for it to slide across my desk. But if my desk was made out of sandpaper and my cup was made out of lead, which is kind of a weird combination, my cup would be really heavy and my desk would be really rough, and it would be much harder to push, that cup across my desk because, the surface is rough. And so that static friction is what we have to overcome in order to move something on the surface. And then we'll talk a little bit about the angled formula. And so now we can, our friction is always opposite our motion. So if whatever direction you were going, the friction is always the opposite direction. So if you are walking down the street, your friction is, the opposite way that you were going, right? If you were driving in a car, the friction on your car tires is the opposite direction. Okay. It's always the way you're not moving. And then this is just kind of a way to remember these movements. If you remember kinetic energy, well, gosh, you guys aren't at energy yet. Well, when you get to energy, kinetic energy will be easier because you'll remember kinetic is moving. So now let's do a kinetic friction problem, and this one is actually an angled problem because I think those are more difficult, and so I wanted to do a more difficult one with you because why not do the hard stuff with the teacher, right? So if we have a block with a mass of 20 kilograms and it's pulled by a force of 150 newtons and we're at an angle of 25 degrees, so that's going to be our theta, above the horizontal, the coefficient of kinetic friction between the floor and the box is 0.15. And it's always, your coefficient of friction is always a really tiny number, even if your sandpaper, you're still going to have, it's going to still be a really tiny number. And so they want to know the force of friction. So here's what we've got going on here. We've got this box and it's on the floor and someone is pulling it, right? I don't really know how to draw a person very well, a person that's pulling things. Okay, let's say this, that doesn't look like makes a lot of sense. But anyway, that's our 25-degree angle. So that's what's going on. We're pulling it at an angle of 25 degrees above the horizontal. So for this one, if you look on your formula sheet, you'll see that there's several force formulas. Okay, and so the friction formula is the coefficient of friction times this normal, or this N force, right? Now we don't know what that N force is, right? They didn't give us that. So then that is going to be your weight times cosine theta. Well, they didn't give us a weight either. So then you can look on your formula sheet and you can see that weight, or Fg, is equal to mass. Oh no, it won't. Mass times gravity, there you go. It won't let me write on the very edge of my screen. So you kind of have to kind of break it down and be like, okay, I've got this, but I don't know that number. Now, how do I get that number? Okay, now I don't know this number. How do I get that number? So the first step is doing your W, which is also Fg. Different teachers call it different things. It doesn't really matter what you call it, as long as you have the you have it right. So our weight is 196 newtons. Okay, now we can take that weight and we can put it in this second formula. Okay. So we can do 196 times cosine 25. Okay. And then you can get 177.64 newtons. Okay. So this one, it kind of has like several steps in it. It's not the speediest problem in the world, but at least each step isn't that difficult, at least, compared to, some of our formulas. So now we can take that 0.15 and multiply it by this 177. I'm worried it's not going to let me fit this. Okay, I'll just do 177. But when I actually typed it in my calculator, I did 26.65 or 177.64. So if you just put 177 in your calculator, your answer might be a little bit off from mine, but it won't be too bad. Come on. There we go. And that would be in newtons. Don't forget your units. You don't want to lose points on the test just because you forgot units. The other thing I want to write, and I'm going to try and put it in like red or something so it's really, really obnoxious, is your calculator needs to be in degrees. The way I can tell if my calculator is not in degrees is when I put something in like a cosine of 25 or something like that, I get like a really, really, really small number right here. And that's how I know my calculator is not in degrees. So just kind of keep that in mind. So that's how you do a friction problem. Okay. And it's an angled friction problem. So it's a little bit more difficult because it has, trig in it. So now we're going to talk about tension a little bit. And I think I have a little instruction sheet. Yeah. Okay. So tension is a specific type of force that is exerted by a string or a rope. Okay. And that's because if let's say you're dangling something by a rope, right? That what makes that rope nice and taut and straight is the tension force. The weight of that thing that you're dangling is keeping that rope really nice and straight. So that's your tension force. Oh, yeah, it's you found it. It should be. I'm not sure where Miss Durden has it. She probably has it on the front page. She probably has it on the resource page. Several places. I'm glad you found it. So, when we do tension, there's a couple things that we do. We assume that all strings and ropes are massless. So we don't really consider the mass of the string or the rope because it's usually so minimal compared to the thing that we're dangling. Okay. And then when something is hanging, the tension of the rope is the weight of all of the objects hanging from it. Okay. So let's say, like in this picture, let's say then we have like I don't know. Let's say that it was possible to like hang another bucket from this bucket. I don't think it is, but let's just pretend that it is. And then we filled up this bucket with rocks, and then we put some rocks in this bucket. The tension on this rope is the weight of all of this stuff dangling. Okay. So let's try a tension problem. In this one, we have I'll use a different color. Okay. We have a 50 kilogram bucket. Okay, that's going to be our mass. And it's being lifted by a rope. They mentioned rope, so we know we're doing tension. I mean, I also told you this was a tension problem, but they mentioned rope. So that's how you know that you're going to have to deal with tension. And the rope will not break if the tension is 525 newtons or less. And so it says that the bucket starts at rest, and after being lifted 3 meters, it's moving at 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? Okay, now, when I typed this one, I forgot to add something kind of important, and that was the acceleration. So I just made up an acceleration, and I'm adding that there. I realized that I started working it out this morning to kind of like practice it. I was like, ooh, this is kind of impossible. So let's talk about our net force. Okay. Um, we can talk about, I know they kind of have a little diagram here, but we've got our gravity force, right? That's the weight of the bucket. And then we have our tension force. And we don't really know, we know that we're lifting the bucket up. So we know that the net force is in the, in the upwards direction, but we don't really know much more than that. Okay. So we'll say that our force of tension is minus our force of gravity. Okay. Now, let's one more second. I had some I was going to tell you, but I want to wait for a second. Do you see how we have this negative here for this FG? That means that you don't really need to mess with your that, like, you don't have to say negative 9.8. You can just do 9.8. We've already kind of taken care of that directionality right there. Okay. If you put a negative in there, it's just going to, mess up the sign on your problem. So I just wanted to let you know that. So your net force or your tension force is going to be that net force plus the gravitational force. Okay. So to get that net force, that's just mass times acceleration. Every time you see F net, it's just mass times acceleration. And then your gravity force is mass times gravity, right? I'm going to move this up here so we have some space. So that's going to be 50 times 1.5 plus 50 times 9.8. And that's going to be our FT. And then we'll have 75 plus 490. Again, that's our FT. And then we'll have 565 newtons for our FT. Okay. Now, they said the rope will not break if the tension is 525 newtons or less. So we got a tension force of 565 newtons. So is our rope going to break? What do you guys think? Okay, well, let me kind of walk you through it. So it says the tension needs to be 525 newtons or less, or it will break, or right? So that means if our tension was 500, it would not break. If our tension was 525, it would not break. If our tension was 2, it would not break. But since our tension is over 525, it's 565, that means this rope is going to break, right? At some point in time, this rope is going to break, okay? Because whatever's in this bucket, or just the bucket, maybe it's just like this crazy heavy bucket, this bucket is too heavy for this rope, okay? And so it's just going to snap.